Okay, so we're going to combine some of what we've learned together into one pretty challenging level problem. The first thing you're going to do is you're going to draw a free body diagram of the two objects. So we have one object on the ramp and one object hanging. Now you're not really going to be able to know which way these objects go because it depends on their masses and the ramp angle. So right now, look at each of their masses. We have an M5 hanging straight down. Then we have an M5 on an incline. So you can compare this downward force to this downward force to decide which one's bigger. Because this one has to be broken into components, pieces, then it will be smaller than this one. So our acceleration is going to be this way. So we're going to call these directions positive directions in our problem. I will leave friction force in my problem until the very end here. So first I know by comparing force sizes that the red block is going to win. So I will draw friction if it existed in this way, opposing the motion of M2. So if there was friction, it would be going this way. I'll cancel it out later when we begin numerically solving. The other forces that exist on this block are a gravitational force and a normal force from the ramp. Oh, wait, one more. We have rope tension. Big deal. Okay. On our pink block, we're going to have mg down, and we're going to have rope tension up. So let's go ahead and write an expression for each one of the blocks. All right. So when we start writing our expression for the blue block, we're going to realize that we have a little bit of a problem because mg is not acting in that same direction as the green forces. So let's go ahead and split it up so that we make our coordinate system work along the ramp coordinate system. So what we're going to do is we're going to break mg up into components that look like this, parallel and perpendicular to the ramp. So let's take mg and we're going to make some of it like this and some of it like this. So we'll have one part going down the ramp and one part going into the ramp. The ramp angle is again here. So this will be mg sine theta. This will be mg cosine theta. Of course, you have numbers, you can plug them in at any point, but given that this is a pretty advanced problem, I'm going to leave them in variable form and you can go ahead and solve back by putting your values in later. Okay, so for the blue block, we'll sum the forces and we'll set them equal to the mass of the blue block times A. So let's look at our forces. You have T pulling up, mg sine theta pulling down, and FF. So you can do T up, FF down, and mg sine theta down. A lot of people forget about this part because it's down here and not directly on the block. Right? So you can redraw it there if you'd like, but you can also just remember to put it and leave it there. Then we go here and we set this equal to MA. Okay, let's go over to the pink block. In the pink block, when we sum the forces and we set them equal to MA, the tension is going to be smaller than mg because this block is going to move down. So mg is bigger, minus T equals MA. Let's look carefully at the two expressions we've made. T on the pink side is a rope that is the same as on the blue side, so that tension is the same. The tension must be larger than the pink, tension must be smaller than the pink block. And this way the pink block will accelerate down. This is the moment where let's look at the friction force expression. If you had friction, which we do not, then what you would say is friction force is mu times the normal. Where do you find the normal force? Well, you have the normal force out of the ramp, and you have mg cos theta into the ramp, and those are balanced. So where you have the normal force, you would write mg cos theta. That's a reminder from our ramp lesson before. For us, our friction force is 0. I'm now going to put that in. So we now have T minus mg sine theta equals the blue MA. On the pink side, we have mg minus T equals the pink MA. So what we can do is we can take these two expressions and we can add them together. So I'm just going to put them underneath each other like this, and then I'm going to add them together. When I do that, I have a green T positive minus a green T. So the T's will cancel out. And then on the left side, I'll have a negative mg sine theta plus the pink mg. And then on the right side, I'll have an MA plus an MA. Remember, these M's are different, right? I'm keeping them color-coded for a reason. They are in this problem each 5, but that won't be every problem, so let's keep them separate. So on this side, we have the pink MG winning and MG sine theta losing, right? And on the right side, you can pull the A out front, so you can do this. Acceleration A, which is the same for both blocks, will equal the blue M plus the pink M. All right, just solving for A all by itself, you can take this M fraction, you can move it over and divide like that on the other side. So this is pretty cool. The acceleration is just the mg, weight pulling down, minus the part of this block that pulls us down the ramp, right, mg sine theta, all over the total mass of them added together. There's another problem on this page up here where there will be a friction force. So follow this technique and see how you do here.